MNU students fall into two categories. Either you went straight from high school to college, or maybe you took a break between high school and college to work or to travel or to, you know, sometimes life happens. We said, suppose there's 1,500 MNU students and 300 of them took a break between high school and college. Imagine randomly sampling 30 students, and then we're going to calculate what's called the sample fraction. Depending on the book you're using, sometimes this is called the sample proportion, but I think, after thinking about it, I feel like the word fraction better captures this idea because it's never greater than 1. In this case, the sample fraction would be the number of students who took a break divided by the total. And what if we did this over and over and over again? Even though we're sampling from the same population, we expect to get a different sample fraction because we're taking different samples. And so the sample fraction itself is a random variable. It's a random variable because we can make statements about the probability of getting one sample fraction or another, but we can't make an exact prediction about what sample fraction we're going to get. So the x in this, the number of students who, find their way into our sample who have taken a break, this is going to be a binomial distribution. But we also talked about yesterday how the binomial distribution is really well approximated by the normal distribution. Whenever the variance is greater than 10. So the way we calculate the variance for the binomial distribution is n times p times 1 minus p. That's the same thing as the variance. And if the variance is greater than 10, then we can also say that this variable is normally distributed because the normal distribution is an adequate approximation of this binomial process. Well, then we can also say that the sample proportion is normally distributed, but since we are dividing by n to calculate the sample proportion, right? The sample proportion is just x divided by n. Well, then our mean is going to be the same, but divided by n. So the mean of the distribution of the sample proportion is going to be that population proportion. Or using the word fraction instead, we could say the mean of the sample fraction is the same as the population fraction. And then this sigma stands for standard deviation, right? So the standard deviation of the sample fraction distribution is going to be the square root of p times 1 minus p times divided by n, all under the square root, because that's what we get if we take the standard deviation of the x variable and then divide that by n. So we talked about this, and I think this was the last thing we talked about last time. As I said, what is the effect of the sample size on the standard deviation of my sample fraction? Do you remember what we said? So if I increase my sample size, how does that affect the standard deviation? It makes it smaller. If n gets larger, because n is in the denominator, it's going to make the standard deviation of the sample fraction distribution smaller, which decreases the dispersion in this distribution for the sample fraction, and it increases our confidence then that the sample fraction we calculate is going to be very, very close to the population fraction. So remember, the game here is we have this population fraction, which is a parameter. And most of the time, we never exactly know what the parameters are. If you do already know what the parameters are, then there's no point in doing statistics. And what we're doing is we are calculating a sample fraction, which is a statistic. And the point of statistics is that statistics are supposed to approximate parameters. A statistic that we calculate is supposed to estimate a parameter that we can never really know, but we're trying to learn more about. And so it's nice if I have a larger sample size, because a larger sample size decreases the standard deviation of the distribution for the sample fraction, which means I have more confidence that I know what the population fraction is more exactly. Okay. So let's ask some questions about this same scenario. If we randomly sample 50 students, what's the distribution of the sample fraction? So in this case, n is equal to 50. P is going to be equal to 300 divided by 1500. And that means P is equal to 0.2. So to figure out if this is really normally distributed or not, we have to do the n times p times 1 minus p, which is going to be 50 times 0.2 times 0.8, which is going to be 8. So is this normally distributed? No. Because the cutoff we decided on was going to be 10. If the variance is less than 10, then we say, no, this is a binomial process that cannot be well approximated by a normal distribution. If it was greater than 10, then we would say, yeah, sure, we could use a normal distribution. But not in this case.
So are you randomly selecting more than 50 from the 300?
No. We're randomly sampling 50 from the 1500. If you knew which 300 of them took a break, and you only sampled from those 300 students, then you'd get a sample where everybody took a break between high school and college. That wouldn't tell us anything about the question. So these are the total number of students in the entire population and the number of students in the entire population that took a break between high school and college. But the game here is this. We wouldn't actually know this number. Okay? If we knew exactly how many students took a break between high school and college, then there would be no reason to ever take a sample, ask the students if they took a break, calculate a sample fraction, right? It doesn't make sense to try to study something you already know for a fact. So the idea here is that since this is a statistics class and not statistics real life, we're peeking behind the curtain and saying, okay, suppose that we know what the population fraction is, and the population fraction would be 0.2. But in real life, we wouldn't know that. In real life, if you already know the population fraction, then there's no point in trying to calculate a sample fraction. Nobody would care. You know, in real life, you only try to calculate a sample fraction if you don't know the population fraction, but you want to know, right? If you're trying to learn those numbers. This is just kind of a backwards example because I'm trying to illustrate what the process looks like. If we randomly sample 200 students, so I'm increasing my sample size to 200, then n times p times 1 minus p would be 200 times 0.2 times 0.8. And that is 32. So that means the sample fraction will be normally distributed with a mean equal to n times p. So a mean would be equal to 40. And a standard deviation and that would be the square root of n times p times 1 minus p. So that would be the square root of 32. You can do that in your calculator. And that is 5.657. So if you were ever to get a question that says, like, what is the distribution of the sample fraction? There's three parts to this answer. There's three things I'm looking for when I grade it. Number one, you need to tell me whether or not this is normally distributed, yes or no. The second thing is, if it's normally distributed, I want you to tell me what the mean of that normal distribution is, because there's a bunch of different normal distributions, so the mean helps me figure out which one you're talking about. And then the third part is the standard deviation, because the distribution depends on the mean and the standard deviation, and then what's the shape of the distribution. It's kind of like normally distributed is telling me the shape of the distribution. The mean is telling me the location. Where is that distribution located on the number line? And then the standard deviation is telling me about how wide or how tall the distribution is. So I need those two parameters plus the fact that it's normally distributed. Okay. Do this one really quickly because it's just like the last one. But it says, we have an evenly weighted coin that we flip. Half the time it lands on heads. If we flip the coin 50 times, we have a sample size of 50. What's the distribution of the sample fraction? So p is 0.5 because this is a coin that we're flipping. We need to test n times p times 1 minus p to see if this is normally distributed. And that would be 50 times a half times another half, which is 12 and a half. That's greater than 10, so yes. The sample fraction is normally distributed with a mean of n times p and standard deviation, the square root of 12.5. The square root of 12.5 is 3.536. Next question. If I were to flip the coin 1,000,000 times, what's the distribution of the sample fraction? So that's going to be a mean of n times p, which is going to be half. Oh my goodness. I just realized I've been making a mistake this whole time and nobody caught me. Whenever I've been answering this problem and the one before it too, what I've been telling you guys is the mean was n times p, like 50 times a half is, what, 25? But that would be the mean of the number of heads that we get on the coin, right? That would be the mean of like the binomial random variable. But what the question is asking us about is really not what's the distribution of the number of heads that we get on the coin, it's what's the distribution of the sample fraction. So let me point out to you again my mistake here. And remember, if you see me make a mistake, you can point it out, let me know. But this is what I've been doing by accident here. And this is what I should be doing, right? I don't care about the number of heads on the coin or the number of students that have taken a break between high school and college. What I'm asked about, what my question is actually asking me about is what's the distribution of p hat? What's the distribution of the sample fraction? So what I should have been using is these formulas. I should have been saying that, well, the mean is always the population fraction in that case. And then the standard deviation is going to be p times 1 minus p divided by n, then take the square root. So I need to go back and fix those. I need to go back and correct that. Like here, in orange, that's still correct. That's still not normally distributed. But here in the blue, when I was looking for the mean, that mean should be 0.2 because the mean is just the population fraction. And the standard deviation is not the square root of n times p times 1 minus p. The standard deviation would be the square root of p times 1 minus p divided by n. So let's try that. That's 0.2 times 0.8 divided by 200. And then I need to take the square root of that number. So this time my calculator is telling me 0.02828. Okay. Huh?
Is there a variance to these?
Yeah, the variance is always the standard deviation squared. So like the variance would just be p times 1 minus p divided by n. Good question. Okay. Now to fix my problem in the purple. The problem in the purple is that I was calculating the mean as n times p, but that's not right. The mean should just be p, because we're talking about the distribution of the sample fraction. And the mean of the distribution of the sample fraction is just the population fraction. Then the standard deviation of the distribution of the sample fraction is the square root of p times 1 minus p divided by n. So now in my calculator, I'm thinking square root of 0.5 times 1 minus 0.5 divided by 50. Okay. So now here in orange, we are talking about the case where we're flipping a coin 1,000,000 times. What's the distribution of the sample fraction? Well, the mean of the sample fraction is not n times p. It would just be p, which for a fair coin would be 0.5. And then the standard deviation is going to be the square root of p times 1 minus p divided by n. So that's the square root of 0.5 times 1 minus 0.5 divided by 1,000,000. And that is 0.0005. So I would say the sample fraction is normally distributed with a mean of half and a standard deviation of 0.0005. That's my answer. And so the difference between the purple case and the orange case, they both have the same mean. They have the same underlying population fraction. And so whenever I take any number of samples, 50, sample size of 50 or sample size of 1,000,000, it doesn't matter. The mean of that distribution for the sample fraction should still be the population fraction. But the difference, the only difference here is that my standard deviation of the distribution has shrunk by a lot. Instead of having a standard deviation 0.07, now I've got a standard deviation of a super tiny number. And I don't know if maybe I need to do a little bit more graphing in this class so you can visualize what's going on. But if I want the normal distribution bell curve here, what I need is 1 divided by the standard deviation times the square root of 2 pi times the, let me think about this. No integral this time. E to the power negative 1/2 x minus the mean divided by the standard deviation. There we go. Okay, so here's my nice bell curve. You can see if I change the mean, make this look a little bit prettier. You can see that if I change the mean, what is it doing? The mean just moves my normal distribution left or right along the x-axis. So the mean is like the center of this distribution. If I set the mean equal to the number 4, then voila, the center of the distribution is around the number 4. The standard deviation does this. If I increase the standard deviation, then I get like a big, super wide, spread out distribution. Like a lot of the probability is spread out over a lot of different outcomes, a bigger range of outcomes. What happens if I try to shrink the standard deviation? I get a smaller and smaller standard deviation. Well, then the probability starts to clump together more towards the middle. Right? So with a small standard deviation, it's really unlikely that I'm going to get an outcome that's far away from the number 4. All of the probability is really concentrated close to the mean when I have a small standard deviation. And whenever I have a large standard deviation, it spreads the probability out. So ideally, if we want an exact value for the population fraction, we want the standard deviation to be super duper 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 small, like that. If you have a large standard deviation, well, then you've got a lot of uncertainty about where the parameter is. Okay, does that make sense? Okay, next. We said this a little bit, but in real life, we don't really know what the population fraction is. If I knew what the population fraction was, I wouldn't need to do any kind of statistics. I wouldn't have to do any kind of survey. But in real life, we know the sample size, how many people are we going to choose. So we know what the lowercase n is. And what we're going to use to calculate this sort of standard deviation of the sample fraction is, we'll use the real value of n, but we have to kind of approximate these values of p. And the closest approximation I can get for the population fraction is the sample fraction. And so while this would be the standard deviation of the sample fraction, this very, very, very similar looking formula is what we call in statistics the standard error of the sample fraction. And we call this a different thing because this is a statistic. It's something we can calculate in real life. And it's supposed to be a good approximation of this. The standard deviation is a parameter that we cannot know in real life. We can't calculate the parameter in real life. We can only approximate it with a statistic. So the standard error of the sample fraction is just the same formula, but you change the p's to p hats. That makes sense? Okay. In an experiment, we randomly sample 30 residents of Olathe and ask them if they recycle. Suppose that we find 24 of the respondents claim that they recycle. What is the sample fraction? It's not a hard question. It's 24 out of 30, which is like 4/5, or 0.8. And then we ask, what is the standard error of the sample fraction? And the standard error is going to be, that number is 0.8 times 1 minus 0.8 divided by n. So on my calculator, I'm going to type in square root of 0.8 times 0.2 divided by 30, close parentheses. I get 0.07303. Again, in this exercise, I don't know what the population fraction is. I don't know how many residents of Olathe actually recycle. But what we've done is we found the sample fraction and said, well, if all I have is the sample fraction, I can't calculate the standard deviation, but I can calculate the standard error. And that's our best approximation of what the standard deviation will be. So now we're moving on to confidence intervals. A 95% confidence interval, you probably heard the word confidence interval before. I heard that a few times, maybe before I took statistics, but if we read this definition, it's an interval along the real number line that contains 95% of the most probable outcomes from a random process that generates a statistic like the sample fraction. And so we are going to have, oops, imagine some real number line. We're going to have some number line, and then we're going to create an interval. Oops. Maybe I didn't label my number line very well, because this is a fraction, so a fraction can only be between 0 and 1, right? And then we're going to have some interval in here and say, well, along this interval, this orange little band contains 95% of the most probable outcomes for the sample fraction. So the sample fraction could be anywhere between 0 and 1, but most likely it's going to be found somewhere in that confidence interval. That's the idea. There's some other definitions that we need to know, like the level of significance. We're going to use this lowercase Greek letter alpha to represent the level of significance. So every confidence interval has a level of significance. And the level of significance is the probability that the next sample we take and the next sample fraction we calculate is going to be outside of the confidence interval. So if I have a 95% confidence interval, the level of significance is 0.05. Because for a 95% confidence interval, there's 5% chance that we're going to end up with a statistic outside of the 95% interval. And 5% is the same thing as 0.05 as a decimal. The next definition says critical value. A critical value is just, it's notated like this. You have z, and then a little subscript is going to have alpha divided by 2. And what this means is, first calculate 1 minus your level of significance divided by 2. And then when you get that number, we need to apply the standard normal distribution quantile function to it, which means calculate the number 1 minus alpha over 2, and then use that number to look up in your table what the standard normal quantile function has to say. And these are called critical values. And all of these are going to be important here in a minute. I'll show you examples. But like, if I wanted to calculate the critical value 0.025. Well, when I look at the 0.025, that tells me that alpha, my level of significance, must be 0.05. That might come in handy later. But I don't really need that to do the problem here, because the problem just relies on this formula. I need to use the quantile function to look up what I get from 1 minus alpha over 2. And alpha over 2 is just the number I find in the subscript. So it's going to be 1 minus 0.025. In other words, I'm going to use my quantile function table to look up the number 0.975. So let's do that. I got it from 1 minus 0.025. So here's my table that you'll have on your test that has the standard normal distribution quantile function. If you don't have one, you can come by my office anytime. I've got lots of them. And we were supposed to look up 0.975. And so here, I see the row with 0.97. And then I also need to add 5 to it for 0.975. So I have to look in this column. Not, I hate this. This column. Try one more time. This column. So the number I'm looking up is 1.96. So this critical value is 1.96. Okay, so how do we construct a confidence interval? 4 steps. Number 1, you have to find out the level of significance. In my example, if we want a 95% confidence interval, then my level of significance is 0.05. We kind of talked about this. 95% confidence means you've got 5% chance that your next statistic is not going to be in that interval. And 5% as a decimal is 0.05. That's what we call our level of significance. Step number 2 is calculate the critical value, which is going to be z with a little subscript alpha divided by 2. In our case, this critical value is going to be the quantile function of 1 minus alpha over 2. So that's the quantile function of 1 minus 0.05 divided by 2. 0.05 divided by 2 is 0.025, which is 0.975. And whenever I looked that up in the table, it was 1.96. So that's step number 2. Step number 3, we calculate the margin of error. And the margin of error is going to be my critical value times the standard error of my sample fraction. And the standard error of my sample fraction, remember, is the square root of p hat times 1 minus p hat divided by n. And then the confidence interval that I'm going to end up writing in the end is going to be centered around the sample fraction that I found. So the lower bound is going to be the sample fraction minus the margin of error. And the upper bound is going to be the sample fraction plus the margin of error. That way the sample fraction lands directly in the middle of the confidence interval, and the margin of error is just the distance from the sample fraction out to the edges of the confidence interval. It's like the radius of the confidence interval. So if we kind of look at this for a minute, my confidence interval is going to be larger if the standard error is larger. So my confidence interval is going to be larger, or wider, whatever you want to call it. I've got a wider confidence interval if my sample size is smaller. Small sample size, big standard error, big confidence interval. We don't want that. We want very small confidence intervals. The other thing too is, the level of significance I choose is going to have an effect. If I construct a 99% confidence interval, it's going to have to cover more of the number line, so it's going to be bigger to capture 99% of the possible outcomes. If I only want a 90% confidence interval, well, then it's going to be smaller because it doesn't have to capture as many outcomes, so it doesn't have to take up as much of the number line. So here's a picture of what this might look like. Remember, the sample proportion that we calculate, that's going to be in the direct middle. That's the center of my confidence interval. And then the confidence interval has a width that's 2 times the margin of error. So here's how we do it. We'll do an example. In the survey, we randomly sample 70 residents of Olathe and ask them if they recycle. Suppose we find that 48% of the not 48%, 48 of the respondents claim that they recycle. Find a 90% confidence interval for the population proportion. So 90% confidence means what's my level of significance? (0.1). 90% confidence means there's a 10% chance that the next sample fraction is not in the confidence interval, and 10% as a decimal is 0.1. So you write alpha equals 0.1 for my level of significance. Then the critical value is going to be z with a little subscript alpha over 2, which is going to be z with a little subscript 0.05, which is going to be what I get if I take the quantile function at 1 minus 0.05, because it's 1 minus alpha over 2. And then that's going to be the quantile function evaluated at 0.95. So let's go pull up my quantile function and find out. What does it say at 0.95? And it has the number 1.6449. So that is my critical value. The next step, after finding the level of significance, finding the critical value, would be calculating the margin of error. So that capital E is going to be equal to my critical value times the standard error of my sample fraction. And so the standard error of my sample fraction would be the number square root of p hat times 1 minus p hat divided by n. By the way, what is p hat? That'd be 48 over 70. That's my sample fraction. And I got those numbers from the problem. 48 out of 70 total is 0.6857. What was my sample size? That would be 70. So that standard error of my population fraction would be the square root of 0.6857 times 1 minus 0.6857 divided by 70, close parentheses. (0.05549). So we're almost there. I just need to multiply 1.6449 times 0.05549. And I get a margin of error 0.09128. And the last step is to construct my confidence interval. And my confidence interval is going to have a lower bound, p hat minus e, and an upper bound, p hat plus e. So I'm going to take 0.6857 minus 0.09128, and I get 0.5944. And then the upper bound, 0.6857 plus 0.09128. So the upper bound, 0.777. Whenever you're doing these problems, it's totally fine if you just want to round to like 4 significant figures on every step. That's what I do for the most part. I'll probably still give you full credit if you just do 3 significant figures, but I wouldn't do 2 because you'll lose accuracy. You'll lose too much rounding error. Yeah?
Where did you get the 0.09128? Like, from the 0.05549?
Oh, this? Okay. I got this number by multiplying 1.6449 by 0.05549. Yep. So how do we interpret this answer? This is my 95%, no, sorry, not 95%, it was 90%. This is my 90% confidence interval. And the way we interpret confidence intervals is a little bit silly. We say if I repeat this process, hypothetically, right? You don't actually have to repeat the process. But imagine repeating the process multiple times, where you gather a sample of residents, you ask them if they recycle, you calculate the confidence interval exactly as we've done according to this method. Then 90% of the confidence intervals that we would calculate will contain the population fraction. Like I said, it sounds a little bit silly, but that's the correct way to interpret a 90% confidence interval. So it should give you about 90% confidence that you have an interval containing the population fraction. So yeah, imagine repeating this process over and over and over from the very beginning, taking another random sample of residents, asking them if they recycle, calculating the sample fraction, calculating the confidence interval, just like we did. Every single time we do that, we're going to have a different random sample. So we're going to calculate a different sample fraction, which means we're going to calculate a different confidence interval. So we end up with all of these different confidence intervals. Maybe we've done the process 100 times. We have 100 different confidence intervals. 90 of those intervals will actually contain the population fraction. 10 of them won't. That's the idea. Okay. So on your homework, where it says exercise 7, how do we properly interpret the 95% confidence interval? We would say, using this procedure, 95% of the random samples of size n will generate confidence intervals that contain the population fraction. And this is the whole idea of statistical inference. You know, the very first thing we did in this class in statistics was descriptive statistics. And descriptive statistics was just a way to describe your data set. Things like calculate the mean, calculate the median, calculate the mode, calculate the sample standard deviation. That just describes a data set. This is what we call inferential statistics. Inferential statistics, like the confidence interval, allows us to make some kind of inference about a parameter, like p. All right, so one more type of problem that we're going to have today, and then we'll be done. It's another procedure for calculating a required sample size. So a lot of the statisticians at Texas Tech would complain that scientists from the other departments, like biologists, chemists, physicists, whatever, they would have already done some kind of experiment, right? Psychologist comes into the statistics department and says, hey guys, I got a grant for $1 million. I already blew all of the money. I already did the experiment. I've already set up the experiment, randomly found my sample group, conducted the experiment. Now I have all this data. And they would come to the statisticians and say, can you help me make sense of this data? Can you help me calculate the confidence intervals? Can you help me do the hypothesis testing? Can you help me do all the statistics? And the statisticians would be mad because a lot of times maybe they didn't select their sample in a random enough way, right? Maybe they selected their sample too conveniently and they didn't try to control a lot of confounding variables. And so their data was garbage, right? You can't use bad garbage, use bad data to calculate statistics, right? Just garbage in, garbage out, that's the idea. And so you've already spent the money on the experiment. Now you've got to go and request another grant to do another experiment where you actually do the sampling correctly. It's good, I guess, to talk to a statistician before you try to do any kind of experiment to get the statistician's input about how you should conduct the experiment. This is one of those things where before we even start to choose a sample size, before we start to reach out to people, before we start to randomly sample our population, how do we determine what sample size we need? Do I need to talk to 30 residents? Do I need to talk to 70 residents? Do I need to talk to 700 residents? This is what we do. Choose your desired level of confidence. How confident do you want to be in your final confidence interval? Because we could choose. We could construct a 90% confidence interval, or if we want to, we could construct a 95% confidence interval. Or if we want to, we could calculate a 99% confidence interval. It's really up to you, the researcher, to decide how strong do I want my final inferential statistics to be. Obviously, this 90% is going to require a smaller sample size. 99% is going to require a larger sample size. So additional confidence costs you on sample size. From your desired level of confidence, we can determine the level of significance. We can calculate the critical value. And then we've got another point where we have to choose your desired margin of error. So before we conduct the experiment, we can decide what the margin of error on our confidence interval is going to be. Do we want a big margin of error or do we want a small margin of error? Small. We want short little confidence intervals with a lot of confidence, right? And the trade-off here is that if I choose a really, really small margin of error, that means I'm going to need a much bigger sample size. If I'm okay with having a wider margin of error, then I don't need to sample as many people. And so there's a trade-off here too. Then we calculate the sample size. I'll show you how to do that, and we round up. because you can't sample a fraction of a person. Okay, determine the required sample size to construct a 99% confidence interval about a population fraction with a margin of error 0.05. Step number 1 is already done for us. Step number 1 says choose your desired level of confidence. This time, let's say we want 99% confidence. So step number 2, we calculate the level of significance, which is, okay, 99% means there's a 1% chance I get a statistic outside of the confidence interval. So my level of significance is 0.01. Then step number 3, calculate the critical value. So the critical value is going to be the level of significance divided by 2. And then we do 1 minus that number, so 1 minus 0.005. And that's what I use for my quantile function. If I look this up in my quantile function table, 0.995 gives me the value 2.5758. Step number 4, choose your desired margin of error. That's already given to us. My desired margin of error is 0.05. And so this is what we do to calculate the sample size. I'm giving you 2 separate formulas. This formula is what we're going to use if we already have conducted a pilot study, or we already know a little bit of something about where the population fraction kind of is. So imagine this, you want to have a super high level of confidence. You want to have a super small margin of error. You know that your sample size is going to be really, really big. It's going to be in like the thousands. What you could do is conduct a pilot study where you only have a sample size of like 50. Go out and you randomly sample 50 individuals, calculate a sample fraction based on those 50, and then that sample fraction is what you use here in this formula. And this formula will then tell you the sample size you need for your actual, big boy study. The one where you actually go out and find 2,000 or 3,000 people. If you don't want to do a pilot study, you can use this formula. This is the formula for no pilot study. But in orange, this is the worst case scenario. The orange formula is always going to give you an n larger than the blue formula. It's always going to tell you need a larger sample size if you use the orange formula. The benefit is you don't have to do a pilot study. The drawback is that it's going to give you a larger number than what the blue formula will give you. Because if I've got p times 1 minus p, the largest value I can get for p times 1 minus p is 0.25. The worst case scenario is that my population fraction is 0.5, because then 0.5 times 0.5 is 0.25. That's the worst case scenario. If I choose any other value of p like 0.1, then I've got 0.1 times 0.9, 0.09. That's a lot less than 0.25. So if you know you're going to end up spending a lot of money, a pilot study is smart in order to reduce your sample size in the very end. Okay, so exercise 9 on the homework. Say something like, I want to know what fraction of Olathe residents own a dog, so I decide to conduct a random survey of residents. If I want a 90% confidence interval with a margin of 0.05 or less, how many residents do I need to survey? So step 1 is already taken care of. I decided I wanted 90% confidence. If my level of confidence is 90%, my level of significance will be 0.05. 1. Now that I have my level of significance, I'm going to calculate my critical value, which is z alpha over 2. And that's going to be the quantile function evaluated at 1 minus alpha over 2, which is going to be my quantile function evaluated at 1 minus 0.05, which is going to be my quantile function at 0.95. So, grab the table, 0.95. Oh, we've already done this one. It's 1.6449. Okay, so we got level of confidence, level of significance, critical value. The next step is to decide how much margin of error that I want to have. And so let's say I want my margin of error to be 0.05. Now I'm ready to calculate my sample size. And in exercise 9, there is no mention of any kind of pilot study. So I need to use the formula that doesn't rely on a pilot study. I need to use the formula n equals 0.25 times the critical value divided by the margin of error squared. So n equals 0.25 times the critical value divided by the margin of error squared. So that'll be 0.25 times 1.6449 divided by 0.05 squared. I got 270.6. But I can't sample 270.6 people, so it would be smarter to say 271. We always round up. So if I want to construct a 90% confidence interval with a margin of error that's less than 0.05 about the population fraction of Olathe residents that own a dog, I know, before I even go out and ask anybody if they own a dog, I know that my sample size is going to have to be 271.